In this program, we're going to introduce you to 3 inventions that open the doors to the infinitely small and the infinitely big. They are the Mercury Telescope, the electron microscope, and the chromatograph.
The first instruments used to observe the stars were astronomy glasses. The first patent for this invention was granted to a Dutchman, Lippershey. He had noticed that a weather vane on a steeple seemed closer when he looked at it through 2 lenses placed a certain distance apart. That was in 1608. Galileo, the Italian astronomer, heard about this glass and perfected it until it was able to enlarge an object 30 times. But we owe the true telescope to Isaac Newton, who invented it in 1670. His telescope was based on light reflection. Rays of light are reflected from a concave mirror, rather than going through a glass lens. From Newton on, all astronomers would use the mirror telescope. During the 20th century, giant telescopes were erected all over the world, but even mirrors could only be made so big. Nowadays, a new type of telescope is picking up the slack, the Mercury Telescope.
About 40 years ago, the technology of glass telescopic mirrors could go no further. The 2 biggest telescopes in the world, with mirrors respectively 5 and 6 meters in diameter, required years of polishing and cost millions of dollars. Moreover, conventional telescope mirrors cannot be made any larger than that. If a mirror exceeds 6 meters in diameter, its own weight and the heat it accumulates during the day would cause it to deform. Such deformations would yield distorted images of the universe. Since the power and precision of a telescope are in direct proportion to the diameter of its mirror, researchers have begun turning to other technologies to build telescope mirrors on a gigantic scale. One such technology uses mercury because of its reflective properties. To convert mercury into a telescopic mirror, it is placed into a circular basin and made to go around in regular rotative movement. A rotative movement makes any liquid take on the form of a parabola. The mirror of a telescope is given a parabolic shape because it thus acquires the property of focusing all the light rays hitting it into one point above the mirror. It is the magnifying power of parabolic mirrors that enables astronomers to observe extremely remote stars, invisible to the naked eye. With the Mercury telescope, the weight of the reflective surface and the temperature it accumulates no longer present an obstacle. As for the toxic emissions from the mercury, they are eliminated by simply adding a layer of oil. The regular rotation of the basin corrects any deformation and continuously restores the ideal parabolic shape. But in order to work properly, the telescope must be completely isolated from all outside disturbances, whether ground vibrations or air movements. As for speed, it must be extremely precise. For this reason, the basin is mounted on a suspension system. The suspension system is an air cushion barely 20 microns thick. That is enough to absorb any vibrations and virtually eliminate any friction between the basin containing the mercury and the mounting holding the basin. The absence of friction allows the speed of the basin to remain constant. But the driving system which makes the basin rotate must also comply with very strict norms. Its motor, rather than being connected to an electric network, is fueled by an independent generator. Any vibration in network electrical current would immediately affect the speed of the engine, and this would alter the parabolic curve. However, the Mercury Telescope has a substantial drawback compared to glass optical telescopes. It cannot be tilted or focused on the star or galaxy you want to observe. Indeed, if the basin were to be tilted, the Mercury would simply spill. This telescope is thus condemned to observe only the stars located in the zenith above it. Furthermore, since the Earth rotates, the stars, which are fixed points in the universe, seem to file past in front of the mirror. This is why all the photographs of stars show shooting stars. The principle of a telescope fixed on the zenith, in fact, only became truly interesting when high-resolution video cameras, which could be paired to a computer, made their appearance in the early 80s. These cameras identify a light point and follow its course. In other words, they compensate for the rotary movement of the Earth. The data gathered by the cameras are forwarded to a computer and digitized. So night after night, the computer's memory records images of the same stars, and this enables scientists to study their evolution. Optical tests carried out with the camera computer system indicate that the Mercury telescope is more accurate than glass mirror telescopes. In addition, whereas the surface of conventional mirrors cannot be made any bigger, scientists believe that Mercury telescopes could be constructed with mirrors of 30 meters in diameter. Such powerful telescopes may finally provide astronomers with the instruments they need to explain the origin of the universe. Man has always sought to establish relationships between the infinitely large and the infinitely small. But for those relationships to be based on scientific principles, reliable observation tools had to be developed. The invention of the electron microscope enables man to make headway in his quest for knowledge about the infinitesimally small. Thanks to the magnifying power of the electron microscope, several thousand times superior to that of the optical microscope, scientists are able to observe the chromosomes of bacteria, discover viruses' methods of reproduction, see the hidden structure of matter. Before the microscope was invented, man knew very little about his environment. Microorganisms, chromosomes, microbes, all this was unknown to him. The optical microscope, direct descendant of the magnifying glass, opened the way to the infinitely small. But the invention of the electron microscope provided the way to greater knowledge about the living and the inert. Today, the very latest electron microscope, the transmission microscope, enables scientists to study the molecular structure of matter with magnifying power exceeding 1 million times. This electron microscope is made up of an electron gun, a vacuum column in which electrons circulate, and a mechanism to insert the specimen to be observed. At the microscope's base, a photographic plate captures the images produced. The images of the specimen, observable through a viewing window, can also be printed on photographic paper or thrown onto a cathode ray screen. All the microscope's functions are computer-controlled, including the degree of magnification and the manifold which creates the vacuum in the column. The magnifying power of the transmission microscope is extremely high, from 300,000 to 5 million times for the top-performing ones. Such a high degree of magnification is due to the fact that the microscope is able to generate an extremely fine electron beam. The source of the beam is a tungsten filament, similar to the one in an electric bulb. But this filament is subjected to 300,000 volts. The electrons emitted by the tungsten go in all directions, randomly. However, owing to their electric charge, they are sensitive to magnetism. To redress the electrons' course and make them converge into a single trajectory, a series of magnets called electromagnetic lenses are placed inside the column. By the time it reaches the specimen, the electronic beam may be no thicker than a millionth of a millimeter. Some of the electrons can thus make their way between the atoms of the specimen being observed and proceed to hit the photographic plate. The specimen, never thicker than 1 micron, that is 1/1000th of a millimeter, acts a little like a grating whose pattern lets the electrons through or blocks them. In this manner, an image can be produced on a molecular scale. The transmission microscope is very useful to specialists in materials, since the mechanical or conductive properties of matter are closely linked to the specific atomic arrangement of every material. For example, the conductivity of superconductive materials depends on the orientation of their crystals. That orientation can be altered by mechanical deformation, by crushing the material. If a specimen is observed under the transmission microscope, the deformation impact on the orientation of the crystals can be observed. Knowledge such as this helps develop optimum manufacturing processes. The transmission microscope can also improve the quality of welding. When 2 plates of steel are welded together, for instance, components in the ambient air, such as nitrogen and oxygen, can contaminate the welding. These contaminants increase the weld's susceptibility to intense cold. By modifying the soldering techniques, the quantities of oxygen and nitrogen in the steel can be reduced. Such impurities can be detected with a transmission microscope. This acquired knowledge helps improve building techniques for drilling platforms in the Arctic, for instance, where temperatures sometimes drop to -60 degrees Celsius. But the transmission microscope also has uses in the biomedical field. Scientists closely observe living matter to discover its microscopic structure. Bone tissue, such as knee or spinal column tissue, for example, are subjected to the scrutiny of the transmission microscope. The goal is to develop new prostheses, in polyethylene, for instance, a material which reproduces as closely as possible the material of ligaments or joints. This research belies the hypothesis that nothing can beat nature at designing the organs and tissue of living things. By revealing the intimate structure of both inert matter and of living cells, the transmission microscope makes a major contribution.
We are constantly venturing farther into the study of the very small, not only to observe it, but also to measure it. Today, thanks to extremely precise measurement instruments, we can isolate and quantify a mixture's components, even if they are only present in the state of traces. This method of chemical analysis is called chromatography. It dates back to the turn of the century. Chromatography was developed by a Russian botanist, Mikhail Tsvet. While trying to separate the different colorings found in the leaves of plants, the pigments appeared in the form of bands of color. Chlorophyll, green, xanthophyll, yellow, and carotene, red. That's why he baptized his technique chromatography, from the Greek word chroma, color. Today, chromatography has little to do with color, but the name stuck.
What's in word there? What and that.
Every day we use and absorb thousands of natural and man-made substances. In some industries, like the food and pharmaceutical industries, it is imperative to know the exact composition of these substances. A highly developed analytical instrument does precisely that, the chromatograph. Essentially, the chromatograph separates the various components of a substance in order to identify them and determine their relative quantities. Provided, however, that the substance to be analyzed can be dissolved in a gas or in a liquid. In a gas chromatograph, the gas serves to convey the solution to be analyzed through the system. For example, the corn syrup used in medical preparations. The specimen is first injected into the system by syringe. Then, under controlled temperature and pressure conditions, the specimen evaporates and mixes with another gas called the vector gas, usually helium or hydrogen. These gases are called vector gases because they convey the solution to be analyzed through the chromatograph. Next, the specimen, mixed with the vector gas, is driven through the column of the chromatograph. In a gas chromatograph, the column is usually made of a metal pipe, the diameter of which is thinner than a hair. Coiled, the capillary column can be some 60 meters long. It is filled with a substance that remains fixed throughout the analysis. That substance is said to be stationary. When the specimen to be analyzed comes into contact with the stationary substance, a reaction occurs. For example, corn syrup used in the manufacturing of medicated syrups contains a number of fatty acids, the proportions of which must comply with government regulations. These various fatty acids are absorbed, thus retained by the stationary gas. However, due to their distinct physical properties, the fatty acids each remain inside the column for varying periods of time. After the fatty acids have been in the stationary substance for a given time, the vector gas pushes them one by one toward the aperture of the column. At the mouth of the column, the fatty acids are captured, one by a detector which measures the relative quantities of the various components composing the corn syrup specimen. The data thus collected is immediately translated into graphic form by a printer. The result? A series of more or less jagged crests. However, these graphs would be useless if not compared to previous chromatographic analyses. These, which serve as standards, provide information as to the duration a given substance will be retained in a chromatograph. Since the retention period varies according to each substance, it is possible to link a crest to a given fatty acid. The calculation of the surface of the crest will, for its part, provide information on the relative quantities of each of the fatty acids present in the corn syrup. There also exist liquid chromatographs, which are used to analyze substances that cannot be volatilized, such as papaya or mollusk flesh. Extremely versatile, the chromatograph can analyze all sorts of products. Today, it constitutes an essential instrument in most scientific laboratories.
Since we began recording discoveries, it is relatively easy to attribute an invention's paternity to a specific researcher. But before there was such a thing as a patent, other inventions were made, just as important, but whose origins remain uncertain. The wheel, coins, vases. What could be more common? And yet one day someone invented a new object, not realizing to what extent it would improve our lives.
Is Al Jazeera.